we're picking up back in Chapter 6, Part 3, and this starts with the 3 different cases of changing an object's momentum. So case 1 deals with increasing the momentum, and one way we can do this is apply a great force for a long time. That's going to produce an increase in momentum, because as you can see by this formula, they're directly proportional to one another. Examples would be both either a person playing golf or a person playing baseball. If either one follows through with their swing or with their baseball, you're going to have an extended time of contact. Case 2 deals with decreasing momentum over a longer time. That's going to give you a smaller force. So, for example, would you rather drive into a haystack or into a brick wall? Whereas you can see by this slide, if your car, this green truck, happens to be out of control, it's much better to hit the haystack than a concrete wall. The physics reason for this is you have the same impulse, but your hitting time is going to reduce the hitting force. And then the third case is when we decrease momentum over a short time. That short interval is going to produce a large force. So anytime you see somebody breaking a stack of bricks, breaking a stack of boards, it's because their hand comes down and hits those boards or bricks for a short time, but with a large amount of force. So now we're going to talk a little bit about conservation of linear momentum. In this slide, you're being presented with a person on a skateboard. So the person on the skateboard, that skateboard's at rest, person's at rest, so because everything's at rest, the momentum's going to be 0. But now, suppose you're going to walk onto that skateboard. Well, when you walk onto that skateboard, the skateboard's going to move in the other direction. Same thing would happen if you fire a rifle. The bullet goes in one direction and the rifle's going to recoil in the opposite direction. So even though we don't know the value of the forces, and therefore the impulses involved, we can assume some things. And the first thing we're going to assume is that there's no net external force to the objects. So no frictional forces. If there are any frictional forces, they're very small, and there's no other forces. So going back to the skateboard, when you walk on the skateboard, there is an interaction. We know by Newton's third law, for every action, there's an equal and opposite reaction. So now with these forces, the time interval has to be the same for the forces that are acting on the skateboard. And there's no way that one can touch the other without also being touched. So basically, you and the skateboard are each experiencing the same force and the same time interval, so you're also each experiencing the same size impulse and the same size change in momentum. Now, we know momentum and impulse are vectors, so we know a vector, direction's very important. So because the impulses are in opposite direction, the changes in the momenta are also in the opposite direction. So the momentum of the skateboard and your momenta are going to add to 0. Now, because the changes in the momenta of the two objects are equal in size and opposite in direction, your value of the total momentum doesn't change. So we say it's conserved. We're going to generalize these findings by saying whenever an object's acted on by a force, there has to be one other object involved. That second object could be in contact or it could be in far distance. So what we do is we consider the objects as a system. So we're saying that whenever there's no net force acting on a system from the outside, that the forces that are involved only are going to act between the objects within the system. So basically the system's isolated, it's closed. So as a consequence of Newton's third law, the total momentum of the system remains constant. And this generalization is known as the conservation of linear momentum. The initial momentum has to equal the final momentum as long as there's no net external force. So basically, I add up all the momenta, I leave, I come back, add them up again. The final and initial are going to equal, even though chaos erupted while I was gone. So another way you experience conservation of linear momentum if you've ever tried to step from a small boat to the dock. As you step toward the dock, the boat moves away. Same effect happens if you're on a big cruise ship and you're going from the cruise ship to the dock. You're not going to see that cruise ship move because of its large mass. So let's try this problem. We have a bullet that has a mass of 0.01 kilograms. So we're going to say the mass of our bullet equals 0.01 kilograms. The bullet has a muzzle velocity of 900 meters per second. You're asked to find the momentum, so we want to know P of the bullet. And you're asked to find the speed if the mass of the rifle is now 4.5 kilograms. So let's first do the first part where we're going to do the momentum of the bullet. So we know that's got to be the mass of the bullet times the velocity of the bullet. So that's going to be 0.01 kilograms times 900 meters per second, which will give us a value of 9 kilograms meters per second. Now we know momentum equals mass times velocity. Therefore, we rearrange and we get velocity is going to be momentum over mass. So our momentum we just calculated is 9 kilograms meters per second, and we're given the mass now to be 4.5 kilograms. So therefore, the speed is going to be 2 meters per second. Now, in this question, why does holding the rifle snugly reduce the recoil effect? Well, if you hold it snugly, you're increasing the recoiling mass because your mass is now added to that of the rifle. So therefore, you're reducing the speed. Okay, another problem, we have a hockey puck whose mass is 450 grams. So by now you know we need to make that kilograms. So 0.45 kilograms. Is traveling at 60 meters per second, and it hits a stationary puck. So we know we're dealing with two pucks. So initial velocity of puck 1 is 60 meters per second. The final velocity of puck 1, first puck ends up going 20 meters per second, is going to be 20 meters per second. The initial velocity of our puck 2, it tells us it's stationary, so we know that's 0. And we want to know how fast the second puck is going, so we want to know the final of our second puck. Okay, we know conservation tells us initial momentum equals final momentum. So let's calculate our initial momentum. So our initial momentum is going to be the initial momentum of puck 1 plus the initial momentum of puck 2. So puck 1 initial momentum, we're going to have 0.45 kilograms times 60 meters per second, plus the momentum of puck 2 is going to be 0.45 kilograms times 0 meters per second. So that's going to give us 27 kilograms meters per second. Now our final momentum is going to be the final momentum of puck 1 plus the final momentum of puck 2. So our final momentum is going to be 0.45 kilograms times our final velocity is 20 meters per second, plus our mass is 0.45 kilograms, and we're solving for our final velocity of the second puck. So that is going to give us 9 kilograms meters per second plus 0.45 kilograms times VF2. Now we know initial must equal final, so our initial momentum is 27 kilograms meters per second. That must equal 9 kilograms meters per second plus 0.45 kilograms times VF2. We solve that for VF2 and we get our velocity of our second one finally is 40 meters per second. Okay. Also, we have conservation of linear momentum when you take a walk. The thing of it is, when you're taking a walk, the something else is Earth, and because Earth has such a big mass, you don't notice it. Okay? Okay, this ends part 3 of chapter